Sorry.
Starting.
Okay, so I will provide a brief introduction. So he's Masataro Asai. He did his PhD at the University in Tokyo under the supervision of Alex Fukunaga. Then he worked at IBM in Tokyo, and then he has been working since as a research staff member at MIT-IBM Watson AI Lab. So his main expertise is on classical planning and heuristic learning and heuristic search. And he nowadays, I would say, mainly focuses on integrating statistical machine learning with the field of automatic plans. The floor is yours.
Okay, thank you very much. Hey, hello, this is Masataro. Okay, all right, so the title that I set up for today's talk may not be appropriate. It may not reflect what I'm actually going to talk. But it has some elements in it, yes. But it's a kind of compilation of my past research and what I've been thinking and what I've been complaining mostly about the what's happening usually in the field of maybe neurosymbolic or neuro along with little bit of everything. So please enjoy. So this is I'm Masataro. Wait, am I out of the camera if I sign it? Yeah.
Please.
Okay. Is this good?
Yes. Okay. Yeah, it's good for the sound and the camera.
And I need to keep in mind about my timing to have 14 minutes, right? Okay, sorry. So first I'd like to talk about the very general research agenda I always have, which is, and then this example is very useful, so I keep using the same thing, although the original reference kind of got very old. So imagine that you accidentally was left on the surface of the Mars, okay? And then so you are this guy. And then you really wanted to go to Earth, go back to Earth. There's some temporary route that you can still live. There are some potatoes. There are, I think, there's a rover that you can operate, but with only for a limited distance, and then you need to recharge it with a solar panel or something like that. And then the final goal is to reach this rocket to go back to the Earth. Well, this is yes. When I first made this slide, it was still a new topic, but I think it's already been 6-7 years, right, since this movie was produced. So it's a reference to the movie called The Martian. I really like this movie as well as the original novel. There are two approaches to solving this kind of real-world task, or hypothetical. But the two approaches. First one is, do you just want to follow what you learned before? Okay. Yeah, you are trained as a Mars, I don't know, space astronaut, whatever. But you are never actually trained to, trained to be left on the surface of Mars. Actually, you are. So the mission is supposed to go without problem. So you only are trained on a specific set of tasks. But there are a certain group of people who believes that training is everything. I really disagree with that. So it's I don't think I'm here, and that's crazy like that. This is type of agent is called a reflex agent. Its behavior is entirely governed by what it has learned before. And I don't have the confidence to say that just relying on what you learned before is enough to survive on the surface of Mars, which is surely an out-of distribution scenarios. The other approach is what symbolic people tend to think about more, which is to kind of sit down, think a little bit more, just chill and adjust, and then create an appropriate behavior. Thinking several steps into the future and then thinking about what will be the consequences validating the idea, and then iterating the trial error in your head first. So that's something called deliberative agents. I pretty much want to build a logical deliberative agent, but that still works in the real world, like based on the real image-based data, or listening, or like talking to people, whatever, reading the article, and so on. The problem with these deliberative approach is that most of the research done for the deliberative agents are symbolic. Well, symbolic systems are good. They are very good at deliberation. Such as, so this example is an 8 puzzle. You move the tiles around so that you complete a puzzle, then you reach the complete picture, like on the right. You can solve this kind of problem well below 0.1 second because they are very good solver. It's optimized, its algorithm is sophisticated, and so on. So it's fast. It's fast, but you assume a particular type of input, which is called a PDL model. So it's a symbolic, domain-specific language for describing the environment. So in this example, it shows an action which says that, well, you can move up an empty tile or a tile into this empty position when a certain condition is satisfied, and then if you use this action, something will happen. Something will change. That's the effect. So it's called action and recognition and effect. So symbolic system, for example, the planning systems assume this kind of symbolic inputs, which is a limitation because they cannot solve outright, solve image-based aid puzzle. Exactly the reason is that we don't have the PDL model. All the system has access to is just the image. Then there's no way that this image contains tiles or that these tiles could move. From at the end, near the end of my PhD, and after joining IBM, I've been keep working on this type of system, which I collectively call Black Plan. Like there are several papers that were produced along the course of study, which address this problem. So the system is not given any prior explicit symbolic knowledge about the environment, yet it processes the image and uses a classical planning solver that uses PDDL to solve the puzzle that was given in images. The key problem solved by that plan is something called the knowledge acquisition model. It's historically, a long-standing problem. So given visual observation on the left, like, okay, something has happened between these two images. You don't know what happened, but something has happened. There are some changes, differences between the one on the left and the one on the right. We have a bunch of these examples. And then, can we learn to produce the PDL model on the right? Can we do that? How do we do that? Well, I figured out that in order to achieve this task, we must automate two processes, one of which is symbol grounding. The symbols means basically the vocabulary that appears in a PDL. So in the case of moving up a tile, so the word move up itself is a symbol. The relationship between the two objects, empty is also a symbol about the predicate. And then there are several types of symbols, and you can see on the table below. Okay, now the system generated these symbols. Is that all? No, that's not all, because now we need not just creating these symbols. You need to associate these symbols each other so that the entire thing will explain some kind of rules that pose in this environment. Such as, okay, in order to perform this move up action, then these conditions must be met. And then if you use this action, then certain changes will happen. This kind of rules. So that is what I call the action model application. Action model learning, that's also the same meaning. That's also used in the literature. Okay, so how do we do it? Like traditionally, the system that outputs the rule, like symbolic outputs, tend to be also symbolic. But now the entire input is based on the image. How do we process such inputs? What we do is basically the discrete representation of learning using the variational auto-encoding technique, or in more general variational inference, because the version that uses the VAE is only the first version in the series of paper. But for the fundamental rule set, we have a variational autoencoder that tries to encode the input image into the latent vector and encode it back to the same image. But the trick is that by using something called the dumbbell softmax VAE, the latent vector converges to a discrete value. Then each cell in the latent vector, like each element of the latent vector, can be seen as a particular type of symbol, in particular the propositional symbol. Well, and then, okay, I don't describe the entirety of the training pipeline, but assume that we already now finished training the entire neural network models. Now, in the test time, when we want to solve a new problem, the system is given two images. Sorry, the image might be a bit too small. A pair of images. The first one is the current status, the beginning of the puzzle, the initial state of the puzzle, which is kind of randomly shuffled state of the 15 puzzle, for example. And the second image is the goal state, the goal image that depicts in which state the system needs to transition into at the end. Okay, given these pair of images, because we have a neural network-based encoder, we encode them into a PDL model, which is entirely symbolic and do not use the human languages. So every symbol that appears in this artificially created PDL file is just numbers. Like if it says Z0 or Z1, then it just means that it corresponds to the Boolean value of the latent vector. First, if the latent vector has a length of 100, then Z0 is the first value in that vector. Z1 is the second value in that vector. And then the value is true or false when the original vector value is 0 or 1. By mapping the input into PDL like this, because then everything is now in PDL, we can use a standard planning solver, which is written in C++ and in C++. It produces a series of actions that is called the plan. But okay, this plan is also symbolic, and the symbolic stuff they are all made up by the neural network, so it doesn't it's not immediately obvious how these plan corresponds to the images. But because the original neural network was an encoder-decoder style network, we can decode them back to the image space in order to understand actually what is happening in the plan. Well, this is a super short version of the short description of what is that one. I have been working on that for 5 years maybe, and then while developing that system, I have kind of have a broader view about how this entire neurosymbolic thing will evolve in the future. Because lots of people are interested in this, I would say also buzzword of neurosymbolic. I wanted to be more specific or more precise. So I came up with this, the architecture, of the rational real world agents. It's a bit bold, but okay, assume everything, everything about the real world or sensor input is supposed to be known. So that's where we are. But eventually, we would always want to map everything back to the symbolic representation, whatever that is. It's not necessarily written in a human language, but it could be associated with a human language. Okay, so that part is already kind of partially solved by that one. because we does the symbol grounding. It maps noisy images into a symbolic representation. But is that all that the neurosymbolic can offer in terms of symbolic problem solving? No, that's not all. The other part is, for example, the search heuristics. Basically, in order to solve the problem, you need to have a guidance about, which direction is better, which direction is bad, which node is bad, which node is good, that kind of measure. This includes in the traditional graph search literature, it's called a heuristic function, denoted by H of S. S is a state, then it's called heuristic function. But in the reinforcement learning literature, it will be written as the p-value function of S, the state. It could be a policy function, pi of A, and also it could be a Q function, whose input is a pair of state and action. Regardless, like all of these provide basically the same thing. It provides a guidance toward how to solve the problem. The other aspects of this, what happens inside the symbolic solver, is the search algorithm itself. There are various search algorithms, A-star, GBFS you probably don't know, but like this is actually the state-of-the-art in plan connecting. And MCTS you probably know because of the reinforcement learning and the AlphaGo stuff. It's super famous, but surprisingly, not many people understand them in the terms of theoretical aspect. And then, okay, the left-hand side could be trained offline using reinforcement learning, supervised learning, semi-supervised learning, supervised learning. Although unsupervised version, I and Carlos tried to work on it a little bit, but the unsupervised version didn't really work. But we might revisit this idea in the future, yes. But I already have a publication for the reinforcement learning version, and the supervised version is the one that we collaborated for his Carlos's thesis. So yeah, heuristics can be learned. What about the search algorithm? The search algorithm part, we can call it online learning because it would use the multi-arm bandits in a tree search context. We could also use we also probably use the dynamic programming and the branch and bound because Esta is basically DP plus branch and bound. Some people are confused if I say that, but the operational research people seems to understand this better. If I call Esta is basically DP and branch and bound. Okay, so yeah, okay, every part covered. Okay, which part can be neuralized? My hypothesis is that the gray part can be neural. Probably the search algorithm part is not neural, but okay. Already we have a paper about heuristic learning and already a paper about symbol grounding. So these two gray parts can be neural. And then the key aspects probably is that they are both are handling something that is the system can be uncertain. And it's also okay to be wrong. So, well, in terms of the symbol grounding, well, humans also make mistakes when tries to understand the real world. So, everything, the PDDL written by human, the PDDL itself could be wrong. Well, because it's written by human, and the human can see the world in a quite distorted manner. Also, the search heuristics provide guidance, and it can be wrong. It's always wrong in some sense. That's why we have a search algorithm that guarantees that the final plan is correct and actually does what we want it to do. So the heuristic itself, the guidance itself, is not supposed to be always reliable. So learning this thing is okay. Right? It can be wrong. For neural network, we really can't trust that. Okay, so this is what I have in mind as a future architecture of everything related to planning. And then I already described that plan. And then yesterday, Carlos already discussed about the heuristic learning with the truncated Gaussian. So today I will discuss the last part, which is about the search algorithm part of and how to make it more related to statistics. well, okay, the talk will contain these aspects. But the important thing is that, okay, over the course of these, like, doing those many studies, I figured out, okay, this is painful. The reason that it's painful is that, like, every time I try to do something new, I found the existing literature very imprecise about the definitions of various stuff. Or like, I don't know, not justify their design decision well enough. That's my impression. That was painful, and then like, because I have to work on 3 different kinds of stuff, and each time I need to look into the literature, like sometimes 50 years ago. I kind of forced to learn about, how to deal with those, how to be sane while doing machine learning stuff. Because I'm originally from the symbolic field, which tends to make sense. And then in the statistical or machine learning, it doesn't make sense. Not always. So yeah. So that's why the title comes in. Where the title comes in. The statistics without care. Yeah, it's very scary because everything looks so fragile, and it doesn't seem to have a solid foundation. So okay, so this please raise your hand. Do you think rate yourself? Do you think you understand statistics? So the 1 star means that you feel like you're just a puppy, and the 5 star means you are confident. You feel like you are bored of statistics. Okay, raise your hand. The 1 star. Okay, 3 stars. I'm going to. Okay. Okay, 5 stars. Who is bold? Who is bold and ambitious? Okay, sure. All right. Yeah. Okay, so for the bold tier, when you formalize a new method, how confident are you? Do you feel you're confident?
Yes, but I think that I'm confident in statistics because if I don't know something, I know that I can understand if I study.
Okay. So, if something that you don't understand comes in, but you are confident that you can understand this.
Yes, I know that it's impossible to know everything about the statistics, but I feel good.
Okay. I'm getting confident, but myself, but not always confident. And then in the beginning, I was I had 0 confidence. Okay, so and as an example, I randomly typed in Google machine learning 101, and then looked at what they would discuss usually. So in the machine learning 101 type article. So this is from a random medium article. So they discuss the mean square regression with a gradient descent, just a linear regression. They use the MSE at the mean square error as a loss function. Right. Okay. What was your name? Aranza.
Yes.
Okay, Aranza. Okay. Well, everyone first learns the mean square error, then learn the mean absolute error, right? Okay. Why they teach MSE first?
I'm not sure, but maybe because it is important to learn the next time and something happen to can interpret it better.
Yeah, the distance is supposed to be added. That's very true. But like mean absolute error is also a distance, and then like it is always positive, right? I don't know why they don't teach mean absolute error first. They could, right?
Yeah.
Oh, is someone no? Why not make mean cubic error? Sorry.
I think it maybe it is to be, but I think the main reason why they increase MCs first is just because it's more common to you.
Yeah, okay, so yeah, momentum, right? Yes, because everyone else has been doing it. Then there must be someone who did it first. So who that, yeah, what this guy was thinking about, well, not necessarily a guy, but that could be an idea. Yeah, why not mean cubic error? Like, not just square, but power to the 3. Why not quadratic error? What's the difference?
Easier to interpret.
How do you quantify the interpretability?
Yeah. I think it's just for results. I mean, people have been trying different errors, and the state of the art says that just give better results. It's not like a demonstration of what I think. I don't know.
I think that for linear regression, the MSE is the simplest error regression that also involves the variance of the estimator.
So that's part of it.
That also involves the variance of the error, like the second momentum.
Oh, yeah, the second derivative is smooth. Yes, okay. I also understand. Is the MQ, like say, quadratic errors, second derivative non-smooth?
Yeah, I think they are smooth, but for a linear regression, I think that you will be only interested up to the second one, like the second momentum of the error.
Okay. Okay, well, actually, I don't know if that's the answer or not, but that sounds logic. Okay, Thursday. What about this one? Mean the partner. So instead of like 3 or 4, it has a pi in the to the power of pi.
Yeah.
It can be anything basically. That's what I'm trying to say. Yes. Like there are infinitely many error formulas, and which one is the best and why? And then why in MMC in particular? This kind of like, if they teach something, it's a result of a choice, right? Then why that choice was made? I was very confused because rarely they talk about it. They intend that article for beginners and then never go further into the details. Another one is variational autoencoder. By the way, how many knows variational encoder? Okay, not everyone. I see. I can skip this slide because I'm running out of time. So it's an autoencoder, but the latent vector is, instead of just a vector, it's maintained as a distribution. When it compresses the image and then decompresses the image, that's an autoencoder. And then variational encoder has a distribution in the middle instead of just a vector. And then there's several questions. Why the prior for the latent vector is unit to 1? Like it's mean 0 and sigma 1. Well, this is actually easy to answer. And then like why not 0 and sigma 2? This is easy to answer because neural network can easily adjust the weights to change that, and then it's almost the same. But why Gaussian? Like why not Laplacian lattice? And then like people don't talk about that much. Yeah. People talk about MAE for regression tasks, but when it comes to variational autoencoder, they rarely talk about Laplacian PAE. At least I haven't seen that examples. Why the difference? And then there are indeed many non-Gaussian PAEs, including the Poisson hyperbolic and much more complicated ones. But they have justification, like they are good at the tree-like structure, or like they are good at the spherical stuff. What is the principle for choosing these different types of PAEs? And then still, most generative modeling literature uses Gaussian distributions. Why is that? Like diffusion models use Gaussian random walk, it's a Brownian walk. But yeah, again, Gaussian. Why? So design choices, they make certain design choices, but it's rarely justified or well explained enough. And in most cases, just follows what usually happens. Because the other paper was also using this, I will also use this type of argument. The final point, the well-studied environmental tend to be very simplistic. Okay, on the left, we see several well-studied topics like classification task. It has a single input and single output. We try to predict the label, which is categorical, from whatever type of inputs. I don't think that there's too much from assumption. VAEs, they are latent. There's a latent vector and the input-output for the X. There are many variants like TCVA, like information, blah, 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 but only two variables. When it comes to multiple connected latent variables with multiple inputs outputs, I rarely see the example. Although these are something that is more probably useful as an application, never saw the solid legend for these. Therefore, I needed to come up myself. Well, this is not what I used in that plan, but the math plan uses the part of this generative model. So it was pretty big. The pain can be seen in this the evolution of lab plan. So lab plan initially was just a simple VAE when I first suggested the idea. But in the next paper, I had two separate VAEs for encoding the image into latent state, as well as another one for actions. In the next version, I made it everything connected and then train it end to end. But as a result, I had to add about 6 loss functions, each one being the KO divergence. 6 losses. And then the final version, I made it predict the forward direction in the time and the backward direction in time. So I made it bidirectional. As a result, the number of lost terms doubled, and then basically there are 10 terms in the total loss function of the neural network. Okay, in this also, you don't even need to look into what is happening in this complex picture because it's too complex. Now, how do we justify such a complex model and its design choices and its loss functions? It's almost like trying to squeeze every part and then try to make it make sense. But how can we do it in a cohesive way? I just found it so painful. Actually, this is, in the end, if you carefully derive the variational lower bound of multiple interdependent variables, then you can eventually derive the lower bound, which kind of makes sense. But in order to do this, you need to understand a lot of stats, lots of how to do it, and the formal side of everything. And then, I don't want to explain everything, but I came to the conclusion that machine learning as a constraint of optimization. I know machine learning as optimization is an established word, right? But constraint is an important part because people really talk about the choice of the distributions and the architecture. So the reason I mentioned that I asked in the beginning about other kinds of constraint programming is yes. So there are many constraint optimization paradigms such as SAT solvers. SAT solvers only have Boolean variables, but other constraint optimization paradigms have several types of variables. The mixed integer linear programming, I guess MIL-P probably people know. They can have real variables and integer variables. In this standpoint, machine learning are similar but have a lot more variable types, including even for the reals, they can be Gaussian or Laplacian or gamma distribution variable. The constraints are usually explained in the MIL-P cases, explained in a linear program, but in the machine learning, I believe it is the constraints corresponding to the graphical model. That the graphical model contains the type of each variable as well as how each variable interact with each other. I can skip this one, but basically the analog applies to every part. Like maximize something subject to blah blah blah, and the subject to part corresponds to the graphical model. I won't skip this slide. And another analog is that it relies on the expert knowledge. When you encode a particular problem into a MathStats problem, then it is done by the expert knowledge. It's from some knowledge base, and then maybe you write a program that converts existing knowledge into SAS formula, or the MLPA formula. But you do the same thing for machine learning, using the expert knowledge. Using the expert knowledge, you define a graphical model. I think this part, the reliance on the expert knowledge, is underappreciated. They believe that they tend to say everything is learned automatically by the machine or the gradient descent. It's not the case. When you need to architect a complex machine learning system, you need to define what dependency exists. And that dependency heavily relies on the expert knowledge. And also the choice of the distribution, whether you make it Gaussian, why do you make it Gaussian? Why do you make it something else? That depends on the expert knowledge. Because expert knowledge represents the correct assumptions. Assumptions are constraints. And especially I have this preference for the maximum entropy distribution under the assumption, because in most cases, if you are given some assumption, then max and under that assumption it tends to be unique. It's not always the case, but it tends to be unique. So it almost relieves me from the burden of arbitrarily choosing a type of distribution. Instead, automatically chooses the distribution for me just by defining the assumption. So you don't do it separately. You choose the assumption that automatically derives the distribution that corresponds to it. So, which is good. I have less things to worry about. The maximized entropy distribution is good because it's most random under that assumption, which means there's no accidental garbage that is accidentally introduced. Only the original assumption, the correct assumption, is followed. Anything else is randomized, so it's a good choice. So imagine you have, 5 cups put upside down, and then one of them contains a coin. An expert says, okay, the coin is definitely in the first two cups, not the rest of the 3 cups. Then now, thanks to the expert knowledge, the maximum entropy distribution is the random flip between the first 2 cups. And you can assign 0 to the rest of the cup. Because that's the most sane scenario. If you assume something else, like if you assign that these 3 also have positive probability, then that's violating the assumption. Also, so the expert only said that it is one of the first 2 cups. If you don't assign, 50% chance, instead if you assign 30% or 70% chance, that's a garbage, unnecessary accidental assumption. So and therefore it's not maximum entropy. Maximum entropy results in 50-50. Personally, something I find it interesting is that maximum entropy often results in a significant interpretable meaning. So, gamma distribution. I like gamma distribution because of the interpretability. Gamma distribution. Do you know much? Okay. Who is confident about describing gamma? Okay. So in a simple word, but it can be explained in a simple word. Gamma distribution of K and theta is the accumulated sum. That's all. Therefore, in a sense, if you are modeling something that builds up, you should use the gamma distribution. The sum of positive amounts that accumulates at a constant rate. Gamma 3 and 4.2 represents, say, the distribution on the wait time of 3 buses. So you need to wait for 3 buses to pass. And each bus comes in every 4.2 minutes. So it's very interpretable. And this, of course, corresponds to the maximum entropy distribution. Okay, now coming back to the original question, we want to explain why regression uses Gaussian distribution by default. It has to do with the mean of Gaussian distribution. What is the meaning of the Gaussian distribution? It's whatever that has a finite mean and variance, and we know nothing else. That's why, like, it's these assumptions. This is a Gaussian distribution, a max entropy distribution for finite mean and variance. These two are the only constraints that is applied when finding the maximum entropy distribution. Therefore, it assumes nothing else. And then that's the least assumption he is making. And that's why, well, finite mean and finite variance tends to hold, although it's not always the case. This is my own explanation for why linear regression, the first course tends to use the mean square error. Large I skipped this, but it's also max-entropy distribution, but also has a finite variance. So basically it has 3 conditions, which is more than the Gaussian distribution. So after getting that kind of basic insight, I believe I myself have the so-called hyperimmunity. I wouldn't be easily surprised by tiny new losses, or tiny new type of neural network or kind of stuff like that. They always try to publish paper which is being forgotten next year, right? So it's a kind of helps me identify which one is more important and which one is not. So hyperimmunity. So imagine you have a certain task you want to solve, and then there comes a new archive paper popping up. They have their own task, and they have their solution that you haven't thought about, and it's hyping on Twitter. What do you do about this? You probably have the urge to apply that to your task. But be careful, right? Well, of course, if you have free time, you can apply. But there's a question mark, because their assumption and your assumption may be different. And if the assumption is different, then distribution that you should use are different, because assumption defines a maximum entropy that results in a different distribution, and so forth. And I will show the actual research that resulted from this kind of insight. Some of the people who attended the EKI this last year really know, but I talk a little bit more further than the understand. So this actually got an award, luckily. I don't know why, but I did. So I did basically, so I still do the classical planning research, which is not necessarily neural, but is made statistical by using the Bartlett theory. So how many knows the MCTS? At least heard about it, Monte Carlo research. Okay. It has been popularized greatly by the success in the game of Go, which is a difficult game. But even before AlphaGo come around. Back then, they used Monte Carlo research, and then they didn't use deep learning, but they have a handcrafted heuristic provided in the MCTS and so on. And then was pretty strong. Monte Carlo research, so imagine that you are playing a game, and then the game already has the initial state. That's the root node, or initial state, or the current state that you're playing. You have this the search tree, basically, that you already thought about in your head before. And then it operates by iterating 4 steps. The first one is action selection. You keep selecting the action left and right at the one of the children until it reaches the leaf node. Once it reaches the leaf node, it expands that node. For example, in the game of Go, from a particular goal state, you have several options where to put your next stone. The expansion generates like a bunch of new states. For each state, for each expanded new state, you evaluate them and assign the score to each new leaf node. And then finally, it backpropagates these distribution upward toward the root, which represents the average of the scores of the children. So the one below the leaf, they have the average of 2 children. In the second level, it basically have the average of 3 leaf nodes below it, and the root node has the average of 4 nodes, 4 leaf nodes. The multi-bound bandwidth is something that is used, algorithm used for action selection in MCTS. So it's about, so imagine that several slot machines. You don't know which slot machines gives you a better reward. So you experiment with each of the slot machines, like a couple of times. And then if you experiment with a couple of times, you have a rough idea of, okay, this one seems good, this one seems bad. And therefore you gradually focus on the good ones. But you don't completely ignore the bad ones. Occasionally you still experiment because the first few calls might be just bad, just unfortunate results, right? So there's a statistical way, like a guaranteed way to how to do the exploration, like trying with the various the arms. And in the MCTS context, each pulling of the arm corresponds to expanding in that direction. So selecting the child of each node. And in the typical MCTS, the backup is done by the average of the children. So if you have 2 children, the parent has the average of 2 children, the grandparents have the average of 4 children, like the grandchildren. Someone about 10 years ago figured out that what happens if we replace the average with the minimum? And it turns out this corresponds to the traditional search algorithm, A-star or DaSCI search, that I assume everyone knows, but probably not everyone knows. How many knows about A-star search? Okay, everyone knows. That's good. A-star uses the priority queue, right? Then if you do the MCTS, but instead of using average, but if you use the minimum, then the single leaf node in the tree exactly corresponds to the priority. And if you keep selecting the action using a minimum, then it expands the nodes in the exactly same order as the standard A-star. This is not my work, but there is this correspondence, correspondence between traditional algorithm and the MCTS. If you replace the average with the minimum, it becomes the same, behaves the same as the traditional algorithm. The problem is that although in games, MCTS is using the average is better, stronger, but in planning, the traditional one is much faster. MCTS is slow despite it's being hyped in games. So what's the difference? So why the difference happens? You really need to think about the different assumptions. Turns out, yes, if you apply the what is hyped about in games naively to the classical planning, it doesn't work because the theoretical assumption does not hold. So in games, they use something called UCB1 bandit. UCB1 bandit is designed for finite known reward. So you can see that, so the mu I is the average of the children. If you are yourself the leaf node, then it is a score of the node itself. The score is basically the win rate. Win rate is always between 0 and 1 because losing is 0. Like 100% absolute lose is 0. The 100% absolute win is 1. So the score is always within a finite known bound. But this really doesn't hold in the classical planning. In planning, this the evaluation function assigned to the score assigned to each node has no known upper limit. It could even be sometimes infinite. So the theoretical assumption really doesn't hold. Okay, how can we modify MCTS to work on this type of score function that could be sometimes infinity? We should use the distribution that supports, that includes infinity range. So the choice is to use something called Gaussian bandit that are designed for Gaussian distribution, which includes the entire real line. This way we can avoid this overspecification. So constraining it within a particular range is an overspecification. We made it larger to avoid that issue. As a result, well, I don't look into the detailed number, but the larger the better. And then this one was much better than both the traditional algorithm and the MCTS done naively. So yeah, the same story. Like when you choose a distribution or apply the statistical machine learning method, choose carefully. There's one more extension of this algorithm because the Gaussian distribution is okay. It's no longer over specification, but it's an under specification. We can do better. Yeah, because it's too wide. Minus infinity to plus infinity is too wide. We know that the score function that we use in classical planning is always positive. So we should be able to do narrower, but without making it too narrow. What we use is to revisit what the traditional algorithm is using. They are using minimum. Then we need to have the statistical version of minimum instead of statistical version of averages. What is the method for statistics of minimum? When you model the average of the data samples, so it looks like this. Each dot is the data point, and then you don't know the actual distribution, but you computing the minimum, computing the average and the standard deviation is same as fitting the Gaussian distribution over it, roughly. How can we instead model the maximum of these distribution? Have you heard about this concept? Not a lot of people know about this. It's usually not included in the textbook. When I write that in the paper and submit it to the machine learning conference, then there's always a specialist that complains it's not obscure ideas, but it is obscure because it's not in the standard textbook. It's called extreme value theory, which focuses on the tail distribution. So imagine picking the top five percentile and then fit a different kind of distribution onto this tail distribution. There are many variants, but one of them is conveniently just uniform distribution, which is super convenient because all you need to do is to pick the minimum and the maximum in the top 5% range. These kind of branch of statistics is called extreme value theory. It took almost a year to figure out what it is for me. And then I managed to come up with a new bandit algorithm. So unlike the previous book, so UCD1 assumes a non-finite lower bound and upper bound. The Gaussian assumes the infinite lower and upper bound. In the uniform, the lower bound and upper bound is dynamically changing. I have a new formula, and I'll perform everything else that was proposed before. This is well, yes. So yeah, if you pay attention on your assumption carefully, then you can eventually come up with the right solution that is supported by the theoretical statistical theory. So be careful. That's the my message. Conclusion: yeah, the UCT was hyped, but it's slow. Why? Because the assumption was not holding. I made the assumption more accurate to the expert knowledge I have about the planning problem task that I had myself. And then eventually the algorithm gets better and better. Because I have the expert knowledge about planning, and then apply that and use that to form the correct statistical modeling. So yeah, don't follow that hype, model the problem correctly. I'm pretty sure I know the time. Yeah, 53 minutes. That's all. Thanks for listening.
Thank you very much. Anyone here have any question?
In the mix between neurosymbolic AI and machine learning models, focusing in the explainability of these models, the symbolic representation of the knowledge might lose some information. So in huge domains, such as, for example, LLMs, such as it makes it more difficult to implement this type of method, like the lab plan that I talked about. In this type of scenarios, are there some relationship between difficult areas such as huge LLMs and this type of neurosymbolic AI? I don't know if I made myself clear.
I also don't know the answer for that, but yes, explain that. Okay, so I intentionally avoided the word explainability because I myself don't understand that well. I also think that the community itself don't understand that word themselves well. So that's that. Yeah, what? Like, okay, if the system gives me the formal statement that is super gigantic, is it really explainable? Well, anyways, yeah, what was the question actually? So,
sorry, I didn't formulate it correctly. If you're trying to make huge models more explainable with approaches such as that plan that you explained about, is it even possible to make it, to implement neurosymbolic methods in huge models?
Okay. Okay, I have two answers. First, my system is not designed for explainability. So I can show you that. Because, so in this PDL, every symbols that are generated are not written in a human language. So even if the human looks at it, there's no way to make sense out of it, even though it's a symbolic model. So being symbolic model doesn't necessarily mean it's interpretable. In this case, I have the first order logical version of this thing extension, but that's also still not that explainable or interpretable. So that's one point. So I didn't design this for interpretability, but it's possible. Okay, so if you have a very huge model, neural network model, which is usually not interpretable, but can we use discrete modeling to make it more interpretable? That's possible. Have you heard about tool format?
Sorry?
Tool format?
No.
So it's well, I think it's getting traction these days. It's a transformer model, but it's trained specifically to use external solver for deriving the answer. Well, external solver being like just a math, like a calculator. So in a sense, instead of trying to, so imagine the LLM prompt is asking for some trivial arithmetic task, like what is 100 plus 45? Instead of LLM answering that by itself, it generates some code to calculator. And then it uses the results that was written by the calculator as an answer. Because LLM itself is unreliable, but LLM most often is able to make a function call in a correct way. Make a function code of calculator and just use the results without modification. So I believe that is one way to provide the explainability, and then a function call is, in a sense, a symbolic, right? Because there's a function name and then there are arguments. You can nest the function. That's kind of interpretable what is happening, right? If it's a nested function. So yeah, this type of like getting the structured input from LLM, that might be one way to get the even if the model is huge, that might be one way to get the interpretable elements from, or making the model more interpretable.
In same line, having account the new visual language model, Japan is working to explore the paradigm. For example, to use him as a encoder, as you are to in order to maintain the same performance about but improve their explainability or interpretability.
So okay, we have the vision language model, and
like if you can change on the diapositives, please.
okay.
Like maintaining that plan approach, but introduce the visual language models to make an encoder, a new encoder that will maintain the plan performance, but improve the explainability and the interpretability of the generated results and plans.
Well, it might be possible with the like fine tuning, right?
Mm-hmm.
Okay. So it might be a bit more complicated, but also the little bit, instead of having data vector, you would have some structure like language input. It's an interesting idea, but like I don't know exactly how to do that, because like in our plan the latent vector is just a vector, but like in language, so if I use the vision language model, then the latent code is in text. Therefore, I don't know how to come up with a say KO diagram. No, okay, I should be able to define a KO divergence between the token distribution, but like that's probably, that doesn't sound right. So anyway, so it's interesting.
Yeah. Previously in your talk, you said that we can see machine learning as learning with the constraint of a practical model, which that practical model, I guess that is the kind of architecture we choose, and it depends on the expert knowledge that we have in the problem. Do you see feasible kind of the future that even determining these constraints could be automatic? If, for example, through a network research or something similar, even trying to choose the proper distributions that fit better to the data?
So basically treating that assumption also as a hyperparameter, right?
Yeah, like you can choose the constraint, not a fixed constraint, but also try to search the constraint.
Okay, someone may do that research. I know some, like there are two factions that who likes that and don't like that, because the people who don't like that is basically who are educated about the statistics from the science side, not the machine learning side, because science side they use statistics to find the answer, while machine learning people are using statistics for prediction. So they are okay with changing the statistical model. So it's more about similar to your approach. Like the distributional choice is also just a hyperparameter. You just find the one that fits the best. That's one attitude toward it. So implementing that kind of system is possible, but how do we interpret that result? Okay, so the architecture search tells you that the one with Laplacian fits the best, but does it really mean that that particular variable has the Laplacian assumption? How strongly can it support that hypothesis? I don't know the answer. It could be also like, it could be just a random seed, right? Like, because the neural network, I don't know, happens. It could be just the size of the network is a tad bit small, too small, or like a bit too large, and then it's overfitting. Like so many aspects affects that. So I don't know if the result of the architectural search would make a conclusion about what latent variable, how latent variables should be. Yeah, it's doable. Yeah.
I'm curious about how you encode the actions in order to solve the puzzles. Because if they are in a latent space, it means that these actions are just for that problem in particular.
Okay, I speak a lot of things about this. Okay, well, this is a test type, right? And then the list of actions in this video is basically kind of the generalization from the training data. Like kind of every type of action that this has seen before is included in this video. So to be precise, what is encoded here is the bottom part of the essence function, which is here. Right? The bottom part is the program file, and the top part is the domain file that contains action. So actually, the domain file part is the same. It can be done once the training is finished, and it's used many times. Like then the part that is generated each time a new problem is given is only the bottom part that has a problem description. So the actions are those actions that apply to any kind of problem, as long as it's the 15 puzzle. Or this particular set of tile pattern. Like this is supposed to make a monkey mind drill image. So it doesn't work if it's a different image, which is sad. But like as long as it's a shuffled version of this mind drill, it works. I hope this answers it.
I have a question. First of all, thank you very much for the presentation, Masa. It was very interesting. So I think one of the key ideas is the use of prior knowledge, constraints, etc., also machine learning, right? Because when we think about symbolic classical AI, the use of prior human knowledge is very prominent. I would like to think, for example, expert systems, right? Mm-hmm. But data-driven approaches, especially now with deep learning, I would say that they don't really like human assumptions. They don't really like a human prior knowledge. They like to learn like everything from data. And I think this is especially Now the case with, I would say, OpenAI's O1, DeepSeek, which are stepping into the realm of reasoning, which is classically, I would say, symbolic, but they say, let's just learn everything from data. Let's just learn everything like with just a small amount of reinforcement learning, not a lot of human priors, not a lot about human even work, I would say, human effort. So playing a little bit of a devil's advocate, imagine that like I'm one of those people that just like data-driven approaches, no human knowledge, no symbolic, no background knowledge. And I say, imagine we have a lot of GPUs, like for example, now with the Stargate project, a lot of funding, a lot of NVIDIA GPUs, a lot of energy, a lot of data, we scrap whole internet. And I say, if we have all of that, all those computational resources and training data, is human knowledge even needed? Is it even good? Why do we care about human knowledge? Let's learn everything from data, just from scratch. So what would you answer to that?
So the human knowledge has a lot of nuances in it, isn't it?
Yeah.
So there are, okay, maybe some human knowledge are holistic knowledge. Like, okay, so say the law of gravity, like relativistic physics law. Physics law does not change regardless of whether a human exists or not. Like it existed before human was born. Those kind of knowledge, do you call it human knowledge or not? So that's one distinction. Like, you know, and then there's another type of really human knowledge. Like humans tend to like, I don't know, having fun, drinking, whatever, party. Right? It's not necessarily true, but like, yes, that's also human knowledge. So when I meant the expert knowledge in that paragraph, I mostly meant more holistic ones. That is like absolute truth about the world or about the data. Like, yeah, do you know what I mean? Like,
Yes,
if you add two positive entities, then the result is also positive, something like that.
But do you think that cannot be done in data? Because, for example, I would say, like, if we do web scrapping, we have like a math 101 course about the University of Granada, and open and let's just GPT reads all that math and say, oh, I now know about the rules of mathematics. So that has been learned from data, low-level data, natural language.
But don't you think you're simplifying it too much? I mean,
yeah, I know.
The main difference between O1 and O3 is exactly the relevance rate, the reinforcement learning with human knowledge. And at the end, what they are doing is using human knowledge in the steps in order to solve the complex mathematical equations and so on. And it's taking, as he said, the knowledge from human activities on that, and is estimating the relevance that is provided by the human using data-driven approaches. But the knowledge, as you said, is a holistic, specific knowledge that the human is injecting, and that's the difference with GPT-4 without O1 and O2. So at the end, the answer to your question would be there is actually need for human knowledge in any way.
Yeah, so I think this is important distinction. So I think it's important to clarify terminology. So I would say like data is also human, right? That data comes from somewhere, from some blog post, from Twitter, whatever. But I would say like most methods only use data, low-level data, some symbolic data like natural language images. And this kind of like assumptions are a different type of data, actually, of knowledge. It is often called knowledge, human assumptions, or they're given like higher level, more abstract concepts. So do you think this kind of like knowledge, information is needed if we have enough data? So regarding the previous question about what about learning this assumption? What about optimizing this, learning this Laplacian and Gaussian just from data?
The sample on the physical laws was a good one, so go for software. So you are doing videos, the videos are working so well because you have data, but then when something is moving inside the video, it's not really verifying the physical laws. So something is missing even if you have a lot of data, a lot of GPUs, a lot of activity.
Yeah, I totally agree, but some people would say like with OpenAI, so now we just need more data. We just need
they're trying to do big models now, but
which is not my approach, right?
No.
And the second approach,
I think Bayesian will tell if the price is correct. then that would drastically reduce the amount of training needed. So it should make it training faster. So therefore, as long as it's a holistic one that's always correct, then it tends to make the training easier, much easier.
But the only important element here is training efforts, like amount of data or amount of computational effort. Is there like another advantage, I would say, of using like this type of grounded mathematical approach instead of just data-driven? For example, interpretability, more like out of distribution generalization, more these kind of things.
I don't know, like say gravitational constant is 9.8 meter per second square, right? There's no point of learning that because we already know the value.
Yeah.
That's my point. Like there are certain things that we really don't need to know, don't need to learn. Like we already know the value. Why not inject that knowledge already in the system?
Yeah, I agree.
If it's possible.
So, of course, I agree on this, but I was like playing the other role. Of course, like, yeah. So that's a very good answer. Yeah, thank you, Master.
Yeah. I think you have a good yes.
Well, it's a quick question. Well, it's a technical question. So here you are using a variational autoencoder to get visual embeddings from these images. And I have a question for you. Well, first of all, thanks a lot for the talk. It was amazing. It was very nice. So how did you exactly go from these visual embeddings to generate the DDDL? I mean, this the arrow with encode. How exactly does it work? Will you repeat that?
Right, there you go. I really need to show the most compressed one because that's the question. Sorry. Can I show only this picture? Okay.
Your favorite screen, I think.
Okay. So the training pipeline is it's always the data is always a pair of images. So something like the one step before something happens and the one step after something happens. So the data is xi0 and like xi1, like a pair of images, ith pair of images, and the first one, the second. And the that's encoded to there, and then so the thing is, this is like a variational inference, and then this diagram includes everything, both the variational distributions and then and the generative distributions. What I figured out is that if I do it and make the diagram that way, then the diagram will look a lot more complicated than if compared to when I only show the generative. Because variational part is kind of alpha, right? Compared to the generative part. So that's one thing I should say. But like so these are a network that so encode the ellipses with the same name are basically sharing ways. They are same neural network. So both images are encoded into a native vector, and then but there's an action network that produces a one-hot vector in the middle. And then so that is let's focus on the top part. There's a KO divergence with a red arrow between AI and the output to applicable. That's sort of work as a. Is it a whiteboard?
No, here it's a bit difficult.
But if you see, Masataro, that it's very complicated, we can discuss this later on via email or whatever.
Yeah, it's okay. Well, but yes, there are many similar bidirectional networks. So each of them produce the native, like latent state-like representation or action-like representation, and then each of them are regularized by other one parts. And then if they are all eventually recorded back to the visual format, and then each of them have the log-like loss to the data, input data. So it has 2 inputs and then 4 outputs about the image. and then a lot more archaeo divergences. Like the blue one is against the prior for the state, and so on. But these losses are derived as a lower bound of the total likelihood for x and x0 and x1. So although it looks complicated, on the math formula, actually, it might, for some people, it looks simple. That's up to debate whether it is simple or not.
Okay. Thanks for the answer.
Can we see the slide of last plan again, the one with,
Which one?
the one so it's previous to this one. It's the one with the red squares showing the difference between the states after the actions are made. This one, yeah. So as far as I understood, the actions are made on the likely space. So I was trying to understand how the real actions that a human will perform are decoded from this Latin space. So what I understand from here is that you must decode each of the internal states of the plan to somehow you have a model that predicts the action performed according to the differences of the decoded states. Right? Yes. So that means the action has to produce a visual difference.
Yes. Yeah.
So it is cool not applied to games or problems that maybe they have an internal state that is not visualized. So maybe there are actions that doesn't make a visual change. Right?
Oh, I see. So I see. Okay, you're talking about the games where
not in this kind of game. Not in
not everything is shown. Yes, that's right.
Visualized.
Yeah. So yes, this assumes perfect information, like fully observable environment. Yes, that's one. Yeah, that's one limitation. Yes.
Okay. Okay. Thank you very much. I'm very happy that I stopped like. Okay. To make it super funny. Okay. So thank you very much.
Yeah. Well, the only regret I'm having is that I'm failing to follow up this line of work with a better code base. I really trying to rewrite everything in PyTorch, which is easy to do, but like I get distracted. More like I try to come up with a generalized version of how to derive the loss function. So yeah, I'm kind of not doing the service of the community about it. So yes, like partially observable extension, I really want to do that, but like yeah, couldn't find time for it. It's a single line.
Thank you again.